Welcome to another video on the igetChem channel where we help you learn chemistry the easy way by showing you how to solve problems. Today's video is on the pH calculation of a weak base solution. So let's take a look at the problem and we will get right to the answer. The Ka of a certain monoprotic acid HX is 3.87 times 10 to the minus 6. Part A, calculate the Kb of its conjugate base, X minus. And part B, calculate the pH of a 0.0475 molar solution of NaX. So first of all, the problem tells you that there is this weak acid HX, which has a Ka value equals to 3.87 times 10 to the minus 6. So just to remind everyone, if you have a acid, when it is dissolved in H2O, it will donate a proton to the water molecules, making them H3O plus, and itself becoming X minus. So in this case, what is the acid on the left side of the equation, or what is acting as the acid, is HX. And then on the right side of the equation, the conjugate base of HX is X minus. So the Ka value is the equilibrium expression for that particular reaction. So you're given Ka, but you want to use that to calculate Kb of the conjugate base, which in this case, as we have said, is this X minus. So let's look at the reaction in which X minus is acting as a base. So let me just write that down. So we want to calculate Kb. So let's figure out what X minus does in water. So as a base, X minus will abstract a proton from water molecules, turning them into OH minus and itself becoming HX. So you see in this reaction, on the left side, X minus is acting as a base, and on the right side, it is producing is conjugate acid, which is HX. So we generally say that HX and X minus is a conjugate acid-base pair because they are related to each other via an acid-base reaction. So in this case, what we really want to do is to calculate the value for Hb given the value for Kb given the value for Ka of its conjugate acid. And we all know that the relationship between Ka of the acid and Kb of its conjugate base is that Kw is equal to Ka of the acid multiplied by its Kb value of the conjugate base. So in this case, we know the Ka value for Hx, and we want to use that to calculate the Kb value of the conjugate base, which is X minus. And of course, the value for Kw, which is the autoionization constant of water, is 10 to the minus 14. So all we would need to do is to calculate Kb is to just take 10 to the minus 14 and divide that by the Ka value for Hx. And from that, we will get 2.58 times 10 to the minus 9. So that's the answer, 2.58 times 10 to the minus 9. So that's for part A. For part B, we want to calculate the pH of a solution containing NaX with a molarity equals to 0.0475 molar. Sodium salts are all fairly soluble, so if you have a NaX solution, it will completely dissolve into Na plus and X minus. So what we are actually doing is that we want to calculate the pH of a solution containing X minus ion, which is basic, with that as its concentration. So to do that, we can set up an IC calculation because this is a weak base. So let me write down the equation again. X minus plus H2O becoming OH minus plus HX So again, initial, we have concentration of X minus 0.475 molar, 0 and 0 for OH minus and HX. And now for the change, we realize that the reaction must go to the right. So all the changes on the right side are positive, and all the changes on the left side are negative. And then we can simply transfer the stoichiometric coefficient down. So this is 1, 1, and 1. So that comes down and give 1x, 1x, and 1x for all three of them. And so finally, for the equilibrium value, we simply apply the change to the initial, and from that we get simply 0.0475 minus x, x, and x. So in this case, the equilibrium constant, as we have calculated previously, for this reaction is quite small, 2.58 times 10 to the minus 9. So the natural thing is to make the assumption that X is very small compared to the initial amount of X minus concentration. And so when the system actually reaches equilibrium, this is simply 0.075 approximately, because the change X is small. But on the product side, we have X and X. So now we can put those into the equilibrium expression. So Kb equals to OH minus multiplied by the HX concentration divided by X minus is equal to X times X divided by approximately 0.0475, and that is approximately equal to the equilibrium constant, which is 2.58 times 10 to the minus 9. And now you can solve for x, simply move this to the right side, and then you will see that x squared is equal to 1.226 times 10 to the minus 10, taking the square root of both sides. This comes out to be 1.11 times 10 to the minus 5. So right here we have x, which is in fact the OH minus concentration, and that is equal to 1.11 times 10 to the minus 5. If you want, you can check that in fact the approximation we have made is good by using the 5% rule. So all you need to do is to check to make sure this change x is in fact small compared to 0.0475, and you see that this number divided by 0.075 is definitely less than 5%. So this approximation in this case is good. Now with that as the OH minus concentration, you can then calculate the H3O plus concentration by using this relationship, Kw equals to OH minus multiplied by H3O plus equals to 10 to the minus 14. Or alternatively, you can actually use this concentration to calculate the pOH, and from that you can then calculate the pH. So let me do that instead of doing it the first way. So pOH is defined as negative log base 10 of the OH minus concentration. So you put that into this expression, minus log base 10, 1.11 times 10 to the minus 5. And so the pOH turns out to be 4.955. So again, a word about the correct number of sig figs to have in the pH or pOH values. So you see right here, after the decimal point, we have 3 digits. And that 3 digits is to reflect the precision in the concentration of the OH minus. As we have said, in a pH or a pOH value, the digit in front of the decimal point has no significance. So finally, you need to calculate the pH, so that's fairly straightforward because pH is equal to 14 minus pOH, because the sum of pH and pOH has to come out to be equal to 14. And so if you subtract 4.955 from 14, you will get 9.045. Again, we have 3 significant figures after the decimal point to properly reflect the precision in the OH minus concentration. So this is then finally the solution. Okay, so this is the end of this solution. And so if you have enjoyed this video, please do subscribe to our channel and like this video.